In this lesson, we're going to do a brief introduction to limits. To start us off, we're going to look at what a sequence is. A sequence is a function whose domain is the set of positive integers and whose range is the set of real numbers. There are several different types of sequences that we're going to encounter. The first is an arithmetic sequence. That means that each term is the previous term plus a constant. So for example, we have 2, 5, 8, 11. The next term would be 14 because we're adding a constant of 3 each time. The next type of sequence we can encounter is a geometric sequence, which means that each term is a constant multiple of the previous term. So here I have 16, then a -8, then a 4, then a -2. So the first thing you may notice is that each term is going down by half, which means we're multiplying by 1/2. The other thing you may notice is that the sign is changing. So that means with every term, I am multiplying by a -1/2. Another type of sequence that we could see is a constant sequence. So that just means that every term is the exact same number. So here we have 1, 1, 1, 1, 1. The limit of a sequence is a unique real number that the terms of the sequence are approaching. So if we look at our sequence and we look at the values as they go from term to term, am I getting closer to a particular value? So let's look at that first sequence, that arithmetic. I have 2, 5, 8, 11. I know 14 is next, then 17, then 20. Well, what's happening with every term? With every term, my sequence is getting larger and larger and larger, and it doesn't look like it's getting closer to any one particular value. So the limit of this particular sequence is infinity. So there is a limit, it's just infinite. That second sequence was geometric. So it was 16, then it's -8, then it's 4, then it's -2. My next value should be a +1, because again, I'm multiplying by a -1/2. Then it's going to be a -1/2, then a +1/4. So sometimes looking at the sequence as a list of numbers may be a little bit confusing. You may not be able to see exactly where that limiting value is, but there is a limit here. And sometimes it helps to see it graphically. So I graphed my sequence here so you could see that here's the number, right? These are my terms of my sequence, and this is my term. So again, I started with 16, I dropped down to -8, 4, -2, 1, -1/2, +1/4, so on and so forth. So I could see as my terms are getting larger, as I'm going more and more terms, the value, the sequenced value, is getting closer and closer to 0. So the limit of this geometric sequence is actually 0. The last sequence that we looked at was the constant sequence. Now you may look at this and say, oh, there's no limit, but there is. It's just the limit is 1. I'm always staying at 1, so the limit of this sequence is 1. Now here's a sequence that actually does not have a limit. So this sequence goes 1, 2, 1, 2, 1, 2, 1, 2, back and forth between these two numbers. So my terms of my sequence aren't getting any larger, they're not getting any smaller, and they're not approaching any number that's in between -infinity or infinity. They're just going back and forth between 1 and 2. So we would say that this limit does not exist. There is no limit for this sequence. So let's look at how this can apply to functions, because that's really what we're going to care about, is the limits of functions. So the limit of a function is denoted as this, the limit as x is approaching a, where a is just a real number, of my function. We want it to equal a value L, where L is just a unique number. Again, it's a real number. It could be positive infinity or negative infinity or anything in between. But the point is that it actually approaches a particular number. And it works very similarly to how sequences do, because a sequence really is just a function. Well, if we look at the function values and we look at them maybe using a table or a graph, that's a way of looking at the sequence of my function values. In order to find the limit of a function, we have to define the left-hand and the right-hand limit. So the left-hand limit is as I'm approaching that value a from the left. So if I'm looking at what's happening as x is getting really close and I'm coming from the left-hand side of my number line, what's happening to the function values? That's what we want to look at. So here's an example. We're going to consider the limit as x is approaching 2 from the left. So notice that the little minus sign behind it means that I'm approaching it from the left, of 7x minus 4. So that means I'm getting closer and closer and closer and closer to 2. What's happening to the function values? Well, we have to look at quite a few function values in order to determine if there is a limiting value. If I just looked at 1.9, I saw 9.3, and then I looked at 1.99, I see 9.93, I would think, oh, they're different numbers, so maybe there's no limit. But if you keep looking and you keep going closer and closer and closer to 2, we can see that the function value is getting closer and closer and closer to 10. And I could see that graphically here. I just graphed my sequence that I have over here, these sequences of numbers. And we could see we started off at 9.3 and we got closer and closer and closer to 10. So it's safe to say that the limit as x is approaching 2 from the left of 7x minus 4 is equal to 10. Next, let's talk about the right-hand limit. So the right-hand limit, it's the same principle except I'm approaching that value a from the right side of my number line. So I'm getting closer and closer and closer and closer from the right. Again, I'm looking to see what's happening to those function values as my x gets closer and closer to a from the right. So the same example, the limit as x is approaching 2 from the right, notice right is the plus sign, of 7x minus 4. So I'm getting closer to 2. I'm at 2.1, then I'm at 2.01, 2.001. Again, closer and closer and closer. What is happening? That function is getting closer and closer to 10 again. That's a good thing. So I could say that the limit as x is approaching 2 from the right of 7x minus 4 is equal to 10. So let's put these two concepts together. The limit as x is approaching a of a function exists if and only if the limit from the left is equal to the limit from the right. So what did we just see? We just saw in our example that the left side of this limit is equal to 10 and the right side of this limit is equal to 10. So we can safely say that the limit as x is approaching 2 of 7x minus 4 is equal to 10 because both of those limits gave us the exact same value. Now, if we were to do this exercise, but we got different values for the left and the right, well then the limit doesn't exist. They have to be the exact same number. So if the limit as x is approaching a from the left does not equal the limit as x is approaching a from the right, then we simply say that the limit does not exist.